Hi, everybody. So this is the motor sizing seminar. There's a couple of documents. If you go to, there's a document called for better motor sizing. There might be introduction to motor sizing, and it's on the California Mechatronics Center website. If you go into the technical documents, I'm going to be referring to this a few times, but it's also something that you can use after we're done, because you're not going to be motor sizing experts by the time we're done here. You're going to have an idea of some of the things you got to cover, but when you first start to do your first motor sizing, you're going to get wildly confused because things are rotating and mechanisms translate, and they gear, and it's actually, once you kind of figure it out, it's not that hard. But at first, people get kind of overwhelmed with what's turning what, especially with all the inertia stuff that we have to deal with. And so what I'm going to do is I'm going to mainly go down through these. There's basically page 1 is called the 7 steps of sizing and selection. And when we get to the motion control part, I'll start there. But before that, I want to do a little discussion of the difference between motor control and motion control. And I noticed that a lot of your projects are going, even though there's a motor involved, you're not really doing motion control. So let me see if I can show you what I mean by that. Let me start out by showing you a thing that you're going to see an awful lot, and that is this is a motion profile, and the axes that we're going to use are on this. We're going to have speed on this axis, and typically I'll use radians per second or revs per second, but in general, already I'm starting to think rotational speed, not linear speed, by using that. And on this axis, we're going to have time. And so typically, motors have to start usually from some 0 speed. So we're typically starting, down at 0, 0. And if you had an application such as, well, let's just take, for instance, let's say you're going to put a motor and you're designing a vacuum cleaner. I don't know, an automated vacuum cleaner. Well, obviously the vacuum cleaner has a motor in it, right? And right now we don't really even know, is it an AC motor, a DC motor? We don't really care what technology. But when you started up your vacuum cleaner, when was the last time you actually paid attention to the acceleration rate of the motor? You didn't. You turned it on and it went. Now, forgive me, motor sizing and motors, you're going to find out sound has a lot to do with understanding what's going on. So I make motor sounds. And so just bear with me, but think about the sound your vacuum cleaner makes when it starts up. It's, and you didn't really pay attention to, was it, which took 3 seconds, or was it, which would actually might have startled you a little bit if it took 300 milliseconds to get started and get up to hold on, let me get some more tools here. To get up to this speed right here, you might have, if that was too quick, it might have actually paid attention to it, but you really don't. And this is because it's not that important in a motor. What's more important in a motor is that it does start and then it gets up to some speed. And then when we started moving along, let's say it got up to some speed here, and we're going through time, the motor's running. This could be, and this doesn't, think of some of the other applications this could be. This could be an auger moving grain around. This could be a pump that's pumping fluid, and not necessarily a metered amount of fluid. What other applications can you think of? I'm thinking like, I'm in my RV. I have a motor, actually I don't, I wish I did. I had a motor, an motorized awning where I push a button, or the slides that go out. You just don't care about the actual how, you know, as long as it takes a few seconds and you're happy, you don't pay that much attention to the speed, actual speed of the shaft and whether it's within a certain percentage. It's just moving. And so this is motor control as opposed to motion control. Okay, so I'm starting out with motor control, and I'm not going to spend very much time on this because the actual equations are pretty simple. You got to get the horsepower right. You probably have to have some starting torque of the motor, but almost intuitively you can probably figure that stuff out just being MEs and in having taken enough physics. So the part that gets hard is when we get over to motion control. So let's finish up with the example of the vacuum cleaner going. One of the other things that you don't really pay too much attention to is the time from here to, you know, where. It's generally until you turn it off. A couple things you didn't really care about. You didn't really care about the velocity in terms of if it didn't have that, if it had sort of this arrangement, you know, if it did that, you didn't really care. In fact, what happened when you got into shag carpet with your vacuum cleaner? It slows down under load, right? And this is actually one of the problems that we've got to deal with motion control. Motor control, it's generally okay to slow under load. And and you don't really care how much between here and here, how much it's controlling, as long as it keeps going. The auger, when it gets a big clump of grain in it, there we go, and it's fine, right? To the extent that it's keeping up. So you're going along in time, and then the last part of motor control is letting it go. So far, actually, you could apply this same motion profile. You could apply this to driving from stoplight to stoplight with your car and aiming for a certain speed of your car, not caring so much if you went over and below a little bit. There's lots of examples of just motor control. So now let's think about what happens as you get out to this point right here. And now it's time, we're done. It's time to slow down. So far, we made the motor have positive torque in the positive direction. These are the, I'm going to call these quadrants. And it helps you figure out what kind of motion you have. Quadrant 1, 2, 3, and by the way, these aren't, there's not a standard for how these are named or numbered, but in general, you have torque on this axis and speed on that axis. So for instance, in this part of the motion profile here, when we're accelerating, you would have, that would be quadrant 1, because you would have positive torque to get it going in a positive direction. Make sense? So that's fine. Then we probably still here are in quadrant 1, unless we, when you start to want to close the loop and control this with servo control, which is kind of advanced, that's when all of a sudden you start to look at these negative torque, positive torque along the way to try and control velocity as the load changes. But that's kind of subtle. That's a ways off. We're not really paying attention to that in motor control too much. So primarily you spend most of the time in getting it going. That's like putting it in drive and stepping on the gas. We haven't stepped on the brake and we haven't put it in reverse yet. So at some point you have to make a decision when you get out to here how to stop. Do you turn it off and just let it coast? And when you let it, when it coasts, as it just kind of coasts down here, you know, at some point it may not even be linear at all. It may go decelerate faster at the end and faster at the beginning, depending on what load is against it. If it's a pure frictional load and it's an even load, it's probably going to be pretty linear. If it's an aerodynamic load, aerodynamic has more force at higher velocity. So an aerodynamic load might cause this to do this kind of, you know, slow quicker as you decelerate. But the point is, right now, we're not, with motor control, you're probably not trying to control. So what I did is let off the gas, essentially, in the driving the car, or turn off the power to the vacuum cleaner. And there's lots of inertia of it moving and some friction, and it generally trades off. If you have a pure coast from here, it essentially trades off all the kinetic energy to heat or potential energy, one of the two, right? So you could, with an AC motor like in a vacuum cleaner, you don't have a lot of choices. It coasts to a stop. When you move to a DC motor, then all of a sudden you can put in some extra controls to it, and you can begin to control its deceleration. For instance, in a electric car. An electric car, you either have the choice of regenerative braking, meaning you're taking the kinetic energy from the device, from all that 4,000 pounds moving down the road, and you turn the motor into a generator, and it creates a voltage and puts it back in the battery, regenerative energy. Or you can take that energy and get rid of it by applying the brake and pulling the energy, that kinetic energy out, and converting it to heat. And then eventually replace your brakes, but we seem to have that down. So amazingly enough, you can do that over and over and over, create heat, and not wear out brakes very quickly. So as you do some loads, you start to pay attention to what happens as you decelerate. What if there's a stop sign? You know, keep in mind that under this curve, the area under this curve here represents speed times time. So the area under this curve represents what? Distance.
Displacement.
How far you went, right? So if you know that you have a fixed distance that you need to go, then at some point you may be saying, ooh, I've gone my most distance. I see a stop sign right here. When I get to that point, there's a stop sign. I had better be at 0 right there. And so now you're starting to think about controlling the deceleration of the motor, not just the acceleration of the motor. And in that case, then you would want to probably, depending on how you're coasting, you may have to start applying negative torque and be down here in this area. And so far, that would be down in quadrant 4, right? If we applied negative torque and now had control of the deceleration rate. So far, we haven't ventured over to this side yet, because this side is when you do what in your car. And in reverse, then, if you were to plot reverse on a motion profile, you would see, and I think I can still do this, you would then see, let's say this is where you stop, you would say, okay, well, we're going to pause for a short period of time, and now we're going to do a reverse move, right? We're going to reverse and back into that spot. And so your overall motion profile would go negative. Your speed essentially would go negative down here. So that's what it would look like if you had a negative motion profile. One of the things that I keep doing is, you'll notice I keep making this motion profile linear. I keep drawing it linear. And the reason is because of the kinematic formulas. Right, you remember what was key, what made those kinematic formulas in physics, where you had, what did you have? You had You had X, you know, V max, and V0. You had time and acceleration, right? So, um, if you're going to make things easy to calculate, the thing to use is kinematic formulas. And so when you start drawing motion profiles, even though you know that when you started up your car, it was not a perfect linear acceleration. Probably pretty close if you modulated it right. The vacuum cleaner, you know, you didn't really care. But as we get to motion control, one of the things that starts to happen is we will start programming that acceleration rate and programming this deceleration rate. We'll have control over it when we move to motion control. And the math is a lot easier when you do kinematic formulas to figure out the relationship between how far you want to go, when you should start decelerating, you know, what speed should you go to make this formula all work and do a motion. So that's really one of the thing we're not going to spend too much time on is motor control, because motor control, you really don't care that much about this area. You're focusing on how much torque, and you're in quadrant 1, and I'll bet you half the applications you have that I saw on the board were just motor control. One of the things when you start to deal with actually choosing motors, here's another graph for you. One of the things you're going to go look at after you've done all these calculations that I'll show you how to do, kind of the end goal is to go find a motor and see what torque it has over the speed range. So for instance, if you look at a combustion engine probably looks something like, you know, probably something like that. There's some maximum, and remember, torque times speed is power. Remember that, right? And so the maximum power point of this may be, you know, is it torque times speed? You know, maybe you develop maximum power somewhere out there, but your torque that's applied to that load is variable over the speed range. A stepper motor has a torque that looks like this. Well, hold on. Don't draw that. A stepper motor has a torque that looks kind of like it transitions a little bit more like that. So this would be a step motor. And there's a couple constraints on this. This one here was combustion engine, right? And actually, this combustion engine also kind of looks like AC motors, believe it or not. They're very similar speed torque curves. Now, there's about a zillion different types of AC motors, and so that's a very generalistic statement that it's like an AC motor, but it is. It's kind of like it. And the difference, if I laid a servo curve over this, a servo curve would probably of the same, we're going to put an asterisk on this curve, same size motor. So servo would probably actually have less torque, but the curve, and this is, let me put same size and continuous duty. You will find that one of the things that I'm going to drill into you if you took my class, and if you probably had me for 140, you probably got the same thing, is that when you see a spec, and I'm going to probably be paying attention to this in your 440 class too. This is kind of an aside, but when you see a spec, you show up and it has, you know, it's 142 PSI, or it's so many pounds, or it's a certain amount of Newton meters. There's a spec on the device that somebody came up with. You always got to ask yourself two things about that spec. You've got to ask, what's the statistics behind how they gathered and presented that spec, and what are the tolerances of it, and then how they did it and reported it are the conditions. Yeah, so this motor here, this motor right here, the stepper motor will give you that speed torque curve. That's the, you know, they give you a line. Well, how many stepper motors are there in the world? How many motor are there of that particular size? Hundreds, thousands? Does every single stepper motor have that exact curve? No, it's magnetics. Some have a little bit less, some have a little bit more, some might have a little bit more friction in them. So in reality, the manufacturer had to decide what curve to publish. And is this going to be the worst case? Or is this going to be a bell curve type of statistical method? Or is this just the average of all the motors? Is it the best one they ever had? They published the speed for that one. That's bad. We hope we don't do that, right? But so you've got to kind of start paying attention to tolerances and conditions when you hear a spec. It's that, because it's not that. What temperature was that taken at? Was that at 25 degrees C? Because we know that, you know, what limits a motor is how much it heats up. And so if you cool that motor down to 20 degrees C, it may be a better speed torque curve. It may be up here. Again, that's the conditions that they ran the test under when they gave you the tolerances and the spec. So you got to kind of make sure that when you're designing along on your project, that you see a number. It's not just a number, that you have to still deal with it and make some judgments about it. Okay, so with all these same conditions, the servo would probably be something like on the same curve, something like that. It would be the reason I drew it so much further out here, and I'm sorry, yeah, velocity. The stepper motor has a lot of, it's got lots of torque at 0 speed. It's really, for the amount of size it has, there isn't a device that has any more torque at these slow speeds, but it's got a complex magnetic structure, and it's lossy, and it loses its torque very quickly. As compared to a servo, so just let me make sure that this is, and I'm going to put servo in closed in, because this is not a hobby servo. A few years ago, the hobby world stole the word servo from us. And now everybody thinks of, if I say servo, they think it's a hobby servo. This is not a hobby servo. This is an industrial servo system. And if you want to see the differences between the two, when you should use hobby servos or when you should use industrial servos, I wrote a article, it's on the Mechatronics Center website, about the differences in a whole bunch of different categories between industrial servos and hobby servos. And because there's a bunch of differences, but they stole our word. So now I have to use the word closed loop, you know, with a brushless motor, or something like that. You have to be more descriptive about it, which is fine. This is one of the things that starts to define. You'll notice that as soon as you go closed loop with the servo, you get a completely different kind of speed torque curve, and that was continuous. But the other thing that you get with it is you get this special line up here. You get continuous and you get peak. You get the ability to overdrive the motor for short periods of time, and that's the peak range, so you can create more torque for short periods of time as long as you give it time to cool down. Other names for continuous are, sometimes you'll see this continuous, that's I do that when I forget to spell it wrong. Continuous, you'll see it, sometimes it's called rated. When you see rated, sometimes you'll see it called 100% duty cycle. Sometimes this will be the RMS, They'll call this the RMS torque. All the same, right? So those are all the same words. The funny thing, the motion industry doesn't have a lot of standard words. And so you'll go from one manufacturer to the next manufacturer, and you'll be trying to read their curves, and they all use different wording. And so part of what you have to do when you first get to the specs is figure out, look at the units, look at the wording, see what kind of wording, how to compare apples to apples. So, okay. Any other questions on motor control before we go on?
Just a quick clarification. So when you see a motor with specs and it says continuous duty on it, that's just describing the conditions of the specs that are listed there. It's not necessarily describing like an attribute of the motor.
It could be either. It could be either. Generally, yes. If it says continuous duty motor, that is a motor designed for continuous duty. An example of something that's not is, for instance, let's say when you get into some mechanics, and you guys have all had 340, so we can talk about ball screws and lead screws, right? So for instance, let's say you're dealing with a lead screw, which is a friction type of nut instead of a ball screw that's a rolling translation. Well, the lead screw, you think it looks at torque and all that stuff, but the one thing that you may see in there is you may see all these specs and then a little tiny asterisk at the bottom that says 40% duty cycle. Like, oh, so kind of the answer to your question is, if they're actually calling out continuous duty, maybe they've got other ones in their line that are not continuous duty that have a limitation on the duty cycle. In other words, usually it's related to heat, it's going to get too hot. But in general, yeah, our words of continuous duty cycle, yeah, that has to do with how hard you can push it for what period of time before it creates too much internal heat that it can't dissipate. Okay, anything else? Okay, so let's go on and do a couple of different, let me give you the overall formula. Let's move on to motion control now, where we're actually trying to control things in different, the quadrants. We're trying to control the whole motion, and you are now programming, probably acceleration. You're programming those parameters that show up in the kinematic equation, and then hoping that the motor actually does that particular profile. You're probably starting to, most of the time, pay attention to distance. And so when we get to motion now, you're probably trying to have either at the simplest end control of velocity. And when I say control, I mean probably plus or minus on a velocity ripple. If you looked at it over time, the velocity of the motor, that you're actually trying to control that to 1% or less. Again, I'm taking that and looking around like 1% and putting that down. It's kind of arbitrary, but in general we are dealing with tighter tolerances on velocity control. Most of the time, you are moving into position control. And position control meaning you are trying to control a motor shaft down to thousandths of a revolution. And if you can control a motor shaft down to fine increments throughout its range, then you can hook it up to linear translation devices, and now you can start to move things in a linear fashion with the ball screw, lead screw, belt drive, cam drive. There's different kinds of conversions, but now you can start to control linear motion down to thousandths of inches or way less. Just as a reference, controlling something to a thousandth of an inch is pretty easy. That's not, you know, it's like, oh, it's only a thousandth of an inch. That's not that hard to do control-wise. The challenge to do any type of precision, or let me use the right words, accuracy. Accuracy almost always comes from the mechanics that you've got in terms of the quality of the mechanics, the tolerances that you're holding as you make stuff, and maybe sometimes as much as anything, the stiffness. So for instance, one of the things that they mention when they talk about a robot arm, you go to buy a robot arm. Let's go buy one of the Omron robots or a dynamic robot. Most of the time, they will give you a spec called repeatability. Sometimes they'll move up to a spec that is resolution. Well, actually, resolution is probably up here. Resolution. There we go. Repeatability. Repeatability is similar in words to what you guys learn as precision. That means the device, once you get it programmed and you get it doing something over and over and over, if you have it move here and move back and move to the same position over and over, it's that kind of automation that you're programming into something. A lot of times all you need is repeatability, precision. It's pretty easy to get that, because if it's not quite where you wanted to land, it went a little bit too far, you go back into your program and tell it not to go so far. Right? But my hands went over here to a keyboard, by the way. I should hold them up for the Zoom. My hands go over to the keyboard. There you go. I'm typing. And so you just tell it, no, don't go so far, back off 4 motor steps. And then you do the move again. Oh, there it is. It's right in the right spot. Boom, boom. And so now you have a repeatable action, and you can program in what looks to be an accurate motion, but the only way you got there was because you had the ability to adjust. So when you move to machines that need accuracy, that's much more difficult. And for instance, when you get to like a CNC or a robot, those are constantly getting programmed to do different things. And if it's trying to go to this position and this position and pick up in random spots, all of a sudden you start to need it to be where you told it to be, and where you told it to be can change a lot. So you switch to needing accurate devices, not repeatable devices. That's almost always based on mechanics, and as you can imagine in a robot, if you had it completely unloaded in the air, it could move to a spot and probably be pretty accurate. But if you went out and pushed on the arm and provided any sort of disturbance or load, it's not stiff. And stiffness, as you know, if you wanted to move something around quickly, you generally have to move things through some series of mechanisms and springs that are between the motor and what you're actually trying to move. And if those things add up to a series of springs, like you would, like your, I think you are maybe have already had all your transfer function stuff, but that's what a transfer function is it tells you, here's the input, here's the output, what's in between, and how's it going to respond? What are the frequencies and the harmonics of it? And the hardest thing we have to do in designing motion control equipment is design in stiffness. It's fairly easy to get things that will move to a separate spot with exactly the same load or with very little friction, very little disturbances. But as soon as you start to deflect something with load, then it's a kind of a much more difficult design. And I suspect that on your projects, if you looked at what's going to actually, you know, make it not work in the end, I will bet you that it has something to do with tolerances that you didn't pay attention to, or the stiffness of the machine. And it's enough of a thing that I wish when you took strength of materials that they would call it strength and deflection of materials, or strength and stiffness of materials, because they're completely different things, right? Some can be really strong and hold a lot of weight, but yet be compliant. Titanium. You think of titanium as this great metal, but it's actually rather springy. It's, you know, you don't see tandem bicycles made out of titanium, because by the time you get out there, they're noodles. But boy, that strength curve just keeps going and going and going linearly. And it for that lightweight, you know, the strength to weight ratio is great, but the stiffness is terrible. So anyway, it's a thing. Okay, so motion control, we're trying to control position of something. And in reality, what you have to remember is that you're going to have some sort of motor at one end, and the motor's spinning, and chances are you're going to have some things in between, maybe a coupler. You may have some gearing, right? And now you're coming off of this shaft. You may have a ball screw out here. So finally out here, you have the mass that you're trying to move. Let's say it's linear, and we'll just draw this. We'll just draw a little ball screw here just for our purposes. So here we have a ball screw. This is the nut. And we've got a little, you know, we got a couple bearings holding it in place. Fixed, simple. You remember those terms, right? A fixed bearing versus a simple bearing. So you may have a thrust bearing on this end and a simple support bearing down on this end over here. So when you start to analyze something like this, and this is a set of gears here, just to get it in the right range. Simple little system. As we begin to look at what we're really trying to control, ultimately, is where this mass is. But along the way, the problem is, in order to control that mass, you had to move this mass, which had to be slid back and forth on a lead screw. And that had to somehow be coupled or attached to a gear, which now had gear slop to another gear, and then was on a couple of shafts, which have rotational deflection. And it doesn't seem like, let's say this is a 1/4 inch shaft on your motor. It's a little stepper motor, NEMA 23. A 1/4 inch shaft, if you put your hand on it, you all messed around with stepper motors when you were dealing with in 140. And you went to grab that little steel shaft, there's no deflection, right? But if you went down and bought a 1/4 inch rod at the hardware store that was 3 meters long, and you put a set of vice grips on this end and a set of vice grips on this end, and you twisted, you could easily twist a 1/4 inch rod quite a ways, right? It has a very predictable, depending on the makeup of the steel, it has a deflection. The trouble that you get into with designing these things is this motor shaft is really short and it doesn't seem like it's going to deflect. But it does, it has a spring constant. So the trouble with doing motion control design, you're trying to do a couple things along the way here. One is you're definitely trying to minimize. You're trying to minimize inertia. So all these parts, this coupler, you would want a coupler that is small and long versus large and short. Large and short, and it means the inertia is all out at the edges and it has a huge inertia. This gear right here, I don't like that gear. That gear has a big inertia. That gear's inertia is probably bigger than this long screw, just because of I squared R. No, I squared R is the wrong thing. MR squared, there we go. Mechatronics, we get to switch, I squared R is power, right? So the coupler, you're trying to minimize inertia, and you're trying to minimize deflection. You would want to look at when you turn this screw. Well, the longer the screw, the more it's doing a rotation. So the thing to keep in mind here is that as we're doing this motion profile and we're doing motor sizing, you are sizing this motor. You are assigning a motion profile. You know, accelerate, decelerate, speed versus time. You're assigning a motion profile to that motor. But in reality, it's what you want the mass to do out here and the pieces in between that matter just as much. So you always got to keep in mind that we're going to do some calculations for what this is supposed to do, but we really only get to control that. And you design, your mechanics are all along the way. This is what you're designing. So the mechanical design is actually as important to a good accurate system as any motor or motion control that you pick, because you can really screw it up bad by going and buying a cheap motor control coupler instead of a motion control coupler. Heavy inertia and lots of wind up because it has a rubber piece in the middle. Boy, we don't want a rubber piece in our transfer function. We wish we didn't even have a transfer function. We wish the motor was the load. And in fact, that's what you start to see more and more. You will see direct drive motors, they call them, or hub drive motors, where a linear motor might be out here. Instead of all this translation, don't do all that. Don't use a rotary motor. Let's just put a linear motor right here on here, and then we'll have direct motion. And we get rid of all those things that cause deflection and inaccuracy. What's the problem with generally doing that? Oh, cost. For some reason, it ends up being motors that you can direct drive loads with are just more expensive than a what I would call this. You guys will laugh. This I would call a hot dog style motor, as opposed to one that was if I was driving the load directly, I would need a lot more torque, because I'm getting torque multiplication in here and here. Whenever I do gearing or ball screws, you get torque multiplication. So this motor here, hot dog style, is a couple of things. It's high speed, and it's low torque. Well, that's all fine, but whenever you have a high-speed motor with low torque, most of the time, if you think of things that you want to move, they're exactly the opposite of that. They are low speed, high torque. And that's what a direct drive motor or a hub motor or you know, those is. In order to get high torque, since torque is R cross F, in this motor here, R is about that, but you have lots of room in the air gap to make force, but the R is small. The other option to make in that motor is to, let's go green. So if we did this style motor, and often this is called, believe it or not, if you called up and asked for a pancake motor, I don't know who started it, but that's what everybody calls it. I need a pancake motor. I need a direct drive is the better word. That is when you deal with R cross F, R is large, right? And so the force may be less, but the R is large. And so you get a lot more torque out of that motor, but it's got a lot bigger bearing. It's a lot more expensive motor to make. Anytime you get a larger bearing and try and hold tolerances at a larger diameter, it gets more expensive. And so direct drive motors, pancake motors are kind of expensive. Linear motors are kind of expensive compared to an easily manufacturable hot dog motor that is high speed and low torque. So we get to control the motor. You're designing all that other stuff to finally control the mass. Make sense? So that's the hard part of this. So just keep in mind that we're almost doing that. We're not doing the actual. We're doing the, you know, the programmed motion that we want. And actual is gonna be different based on the transfer function of this.